Hello everyone. The topic of today's discussion is waveform shaping circuits. So in order to understand what waveform shaping circuits are and how do we analyze these, we will be doing an example to demonstrate how do we analyze waveform shaping circuits. So here we have been given that we have a circuit with a diode, a resistor and a 3-volt battery, and we are asked to determine the output input relationship, which means that when the input varies from minus infinity to infinity, what is the value of the output? Basically, how do we express output as a function of input? That will be the output input relationship of the given circuit. And we are being given that the diode is an real diode with a cut-in voltage of 0.7 volts, which means that when the diode is on, it will behave like a battery of 0.7 volts between the P and N terminals. So in order to find the output input relationship, what we will do is we will vary the values of the input from minus infinity to infinity. So just for convenience, we would vary the input from minus 5 volts to plus 5 volts to capture the changes in the circuit or in the output input relationship when we vary the input. So let's say we have the input voltage at minus 5 volts. So there can be two conditions whether this diode can be on or off. So we assume that the diode is on for time being. So when the diode is on, there will be some current flow through the diode, and the current flow direction in the resistor will be in this direction. So since this is minus 5 volts and current flows from higher potential to lower potential, the potential at this node will be less than minus 5 volts. And this potential is fixed at 3 volts. When we give this node as a reference potential of ground, we can tell that this potential will be 3 volts. So the potential across the diode is minus 8 volts, which means that the diode is actually off. So the assumption that we made about D being on is incorrect. And the correct state of operation of D is that it is off. So when D is off, it will behave as an open circuit and there will be no current through the diode, which means that there will be no current through the resistor, which means that there is no IR drop across the resistor, allowing this potential to be exactly equal to the input potential, which is minus 5 volts. So output was equal to input at input being minus 5 volts. Now let's say we increase the input to minus 1 volts. Now also we may assume that diode is on and we may say that there is some current flow through the diode, which means that current flows in this direction, and again this potential will be less than minus 1 volt, and this is clamped at 3 volts by the DC battery. So again this potential is minus 4 volts, and again we may say that okay, D is actually off and the assumption that we made is incorrect. And when D is off, again the same story, this is an open circuit. Since we can replace it by an open circuit when D is off, there will be no current, there will be no IR drop, and hence this potential will be exactly equal to the input potential. So this condition will also hold true at minus 1 volts. So naturally there will be some turning point of the circuit where the operation of this D will go from off to on. You can keep doing this, but at some point, at some input value, this relation will no longer hold true because because the diode will change its region of operation from off to on. Which can be intuitively seen by the fact that as you keep increasing this voltage will also keep going up, and eventually the positive terminal of the diode will keep on growing. And since the negative terminal is fixed at 3 volts, at some value of Vi, this diode will turn on. So we wish to calculate at what value of Vi the diode will turn on. So when the diode is just on the verge of turning on, the IV characteristic of the diode can be plotted, and it is something like this, where this is the cut-in voltage of the diode that is given to us as 0.7 volts. So just when the diode starts to turn on at this potential, the current through the diode is zero, just when the diode is on the verge of turning on. So we may assume that the current through the diode is zero just when it starts to turn on. So the current through the resistor will also be zero. If this is Vi, then this will also be Vi, and this is clamped at 3 volts. So we may say that this potential is Vi minus 3, and in order for it to conduct, it should be greater than the cut-in voltage, which is zero point 0.7, which means that Vi should be greater than 3.7 volts. So you can keep doing this till Vi equals to 3.7 volts, and after that D will conduct. So for this value of Vi, D is off, and for values of Vi from 3.5 to 5 volts, D will be on. So when the diode is on, we can replace diode with a battery of 0.7 volts between the P and N terminal, with the positive terminal at P and negative at N. And since this is 3 volts, this is ground, this potential is 3, and this potential is 3.7, and this was Vi. So for Vi greater than or equal to 3.7 volts, the circuit condition will be something like this. this potential will be held at 3.7 volts regardless of the value of the input voltage. And what will change is the current through the resistor, which is equal to the current through the diode. That will be a function of Vi, and it will be given by Vi minus 3.7 over R. So what we made out was, if we have a sine wave which oscillates between plus minus 5 volts, what we got to know was for Vi less than 3.7 volts, D is off and there was no IR drop, so output was equal to input. And when Vi becomes higher than 3.7 volts, the output is equals to 3.7 volts since the diode becomes on and we had the two batteries in series. So this was 3.7 volts and here we had the diode being off. So there was no IR drop across the resistor. So the value of the input was exactly reflected as the value of at the output. So when it is less than 3.5 volts, it follows the input. And when it is greater than 3.5 volts, it just sort of clips as if you are having a scissor and you clip the values of the waveform which are greater than 3.5 volts that are clipped. That's why this circuit is called as a clipper circuit, because it clips or cuts down the values of the waveform which are greater than 3.7 volts and they are held at 3.7 volts because of this.